So what we are going to look into today is a short introduction to COMSOL multiphysics. What is the model manager, different motor and generator designs, and how can you utilize the part libraries? It's one of the new features here in COMSOL. How you can couple AC/DC to heat transfer. That's also possible here since we are dealing with current, sometimes high currents. It's essential to include that in your simulation. And also how you can calculate losses and different optimization solutions. So how you can combine optimization with an AC/DC module. And some further steps to the rotor dynamics and co-simulation. So how to achieve that and what is available there. So here you can see the current snapshot of the portfolio of COMSOL multiphysics. So the core COMSOL functionality includes all the linear and laminar regime for structure mechanics through electrostatics, heat transfer, and fluid domains. You can use the built-in application builder to create standalone applications. So that's available with core COMSOL functionality. And you can use the model manager to store your assets in a nice and neat and convenient way. You can also use COMSOL compiler to compile your finite element models into applications. And you can also use COMSOL server to store your applications. So if you want to share it with others, with colleagues, you can use that at remote places from an Android client. That's also possible with that. And on the physics side, so currently we are focusing from the electromagnetics branch on the features of the AC/DC module. So basically we will utilize those features that are available here. And we also look into different sections of the heat transfer module since we have losses. So it will generate some temperature rise. That's essential to incorporate into your model. Even we can do that with COMSOL multiphysics. And you can also include the CFD module. So if you need to add some active cooling onto your model, that's also possible to use this with the CFD module. And we are dealing with rotating machinery, sometimes high-speed machines. Then you can use and you can extend the capabilities of your AC/DC module with the rotor dynamics module. From the software side, in COMSOL, you can combine and couple any number of physics into true multiphysics applications. And these motors and generators, yes, they are true multiphysics applications. So on top of the Joule heating, which generates heat, then you can use the rotor dynamics module to calculate, let's say, the Campbell diagram of that machine and the bearings. So you can add different bearings. You can see what happens if you set up different eccentricity for different bearing types, and you can see the orbit during operation. And then you can add the fatigue module to calculate or make an estimation of the life cycle of your device. So that's also possible on top of the electromagnetic and heat transfer simulations. And you can also further extend with an acoustics module since we have some misalignments, vibrating housing packs, so they can generate noise. So you can use the features from the acoustics module to use and incorporate into your model. So as we have seen earlier, so we can introduce and we can include our models into the model manager. So that's a very nice and convenient place to store your models, store your assets and digital files in one place. So it can be stored in a local database. So this database can be created inside your computer. It can be placed on a remote drive, and you and others or other colleagues from your organization can access these assets quite easily. You can set up tags. It's super easy to do that. It has a very quite nice and very powerful search engine. So you can search for boundary conditions, for physical setups, for any parameter essentially that lives inside the COMSOL model. So what do we have here for the electrification cluster in COMSOL 6.1? What news do we have here? So from the battery side, we have the battery packs and the modeling and more convenient way of modeling of thermal runaway. We have some updates for fuel cell simulations. And what we are looking into for today's webinar is for electric motors and generators. So we have some updates to motor winding layout. That's a new feature here in COMSOL. and also this magnet arrays. That's a quite nice feature, and it can extend and make your work more efficient. So from electromagnetic side, so here you can see on the right side a small animation. That's a nice motor model that's still under construction, but soon it will be available at the model database. So you can use this tool for automatically create motor windings and then magnet arrays. It's super easy to use, and there is a new multiphysics node, which is the magnetohydrodynamics multiphysics interface for liquid metals. So if you want to include such models now, that's also available here. And some updates for the RF module, but that's not that essential for here. Okay, calculating losses. So there are different ways how you can calculate losses in COMSOL multiphysics. So based on the Bertot and Steinmetz versions, you can also use always the user-defined version. So in most interfaces, in most cases, the user interface is prepared to use some sort of user-defined expression. So here in calculating losses, that's also available. And you can use a time-dependent simulation, then you can use an FFT to check for harmonics in the signal. That's easy to do. You can also add active cooling. So here you can see a motor, and you can see solutions from two different versions. One is for where we don't have active cooling, so we neglect the fact that we need an active cooling, and this stands the maximum temperature climbs to 160 degrees of Celsius. And then let's say we decided, yes, we need an active cooling, so we add features from the CFD module, and we can expand the complexity here, and then with a certain tuning of the parameters, now the maximum temperature drops to 100 degrees of Celsius. So that's one extension that can be made up here with an active cooling setup. We can also add, and we can investigate the vibration of the housing, what happens when we have some misalignments from the bearings. And here you can see three snapshots from the left, starting from the left. So we have the stress distribution in the housing. So here we expanded the model. So we used an AC/DC simulation to calculate the forces that will be acting on the bearings and the shaft. And that is transferred through the housing of the electric motor, as you can see here. And in some portions, it's a thin shell element, and some portions are thick plate. So different theories can be used here. And then we have the bolts that hold down the housing to the ground, and you can extend the features for that one. So you can see what will be the stress distribution during the operation of the motor. And you can also plot here on the right hand side, you can see this orbit plot for the two bearings, so you can see how the positions of the two bearings will change during the run-up of the motor, so you can extend the capabilities with this bearing simulation. So on top of electromagnetics and heat transfer, you can also include this rotor dynamics applications, and a structure. You can calculate the structural deformations of the housing. Magnetostriction, that's also available. So yes, when you are walking through the street and you go through a transformer station, walk by a transformer station, you can see that humming noise that's coming from that device here. That's the magnetostriction that's causing the humming noise. And that's also possible to model and simulate in COMSOL multiphysics. So this is our model here. So we will model this induction motor here, and with different pairs, different magnet arrays, with different scenarios, different phases, and yeah, jump into COMSOL. Let's see how the model is set up and how you can use that one in your simulation. So let me go to COMSOL multiphysics, and here let's start with the geometry parts. So here, if we go to Windows and part libraries, then here you can see all the available models, all the available parametric geometries that are suited for your use and incorporated in the model. So it's grouped to core COMSOL functionality, and what we are looking into the library that comes for the AC/DC module. So here, yes, we can coils, cores, and here you can see rotating machinery 3D. So let's jump into that one. So here you can see there are different parts for different setups. There are different arrays in 2D and in 3D also. That's what we have seen previously. So you can just click and import to your model. So you can have a very nice starting using your motor simulation. The game, the same goes for stator parts for 2D and 3D as well. And you have the same setup with 2D. Usually you can start the modeling in a 2D version, then you can expand the model to a 3D version. So if you are satisfied with the 2D setup, then you can jump into and start using more complex, more detailed 3D versions. So yes, we follow the same workflow here. So we start with the 2D representation of our motor here. So here we have an internal rotor that's imported from the library, as you can see here. And we have the same stator imported from the library. So we can easily add a geometry here. So if we go into the geometry node, as you can see, we have two import nodes here, importing the two sections. They are parameters, as you can see, so you can click and you can delete, overwrite, whatever your choice is. So it's quite easy to do that. That's the geometry side. That's quite easy to set up. That's nothing special here currently. From the material side, yeah, different domains have different assignments. So this one is assigned to air. So these are the soft iron regions. This is for the copper part, for the magnets, and for the iron part. That's the shaft here, technically the shaft. From the motion to set up the rotating motion. So we have this rotating domain node here. So we have an angular velocity set up. So this will rotate the internal part of our model. Going back to the physics interface. So we have one rotating machinery magnetic physics interface here. And what we have here and what's the most important is let's start with here with this BH iron regions. So this part is defined by the BH curve, which is set up in the iron part. So if we go into our material selection and we go to iron, soft iron, then here we can say that this is the BH curve defined here. This is an interpolation curve. It can be imported from a measurement or any other data, numeric data can be imported. So this is the curve that we are using during our simulation here. And then we have a subnode here for the iron part. So we are using that subnode for the loss calculation. And as we have seen in the previous slides, so we have the Bertotti, Steinmetz, resistive heating, and also as always the user-defined version, so we can use that one. Conducting magnets, one of the new features here in the 6.1 version. So you can set up the north and south boundaries of the magnets, and COMSOL will align all of the other magnets according to that one. So it's in a circular pattern. Yes, it can be also a linear one if you are dealing with linear motors, and it's a repeating periodicity, but it can be alternating or user-defined. The center is in the Norigo in 0.0, and you can define which is the north and which is the south part of the magnets. That's all the setup that we had to do. And there is a new multi-phase winding feature. So you set up the parameters and it's set to automatic 3-phase. So COMSOL will automatically set up the 3 phases and assign each domain to the correct phase with the correct shift. Number of poles, number of slots, parameters as always, and how many coils per slot do we have. And here in subnode settings, here we have the automatic phases. It's totally automatic setup phase 1, 2, and 3. And here we have the same setup for each phases where the current is reversed, the flow of the current. And we also have, yes, the loss calculation for the windings. Okay, and we have a torque calculation, so we can calculate the torque, the magnetic torque here. So that's from the physics setup. And here we can see the torque, how it's changing, and the density, the flux density, how it's changing through the thickness. And here we can see the losses. That's the calculation for that part. And since we have some losses, and we can add the heat transfer quite easily. So we can add, right click and add physics, heat transfer in solids. And then you can add a fluid interface where you have fluids. Then you should set up this one in this sense. So here we have where we have air, like here in number 8 and 27, 28. So we can set up the fluid domains there. So it's 8 and 27 through 28. So these are the fluid domains. And then we could set up heat flux on the outer boundaries. And instead of manually clicking all of these little segments here, so we can set up a selection, an explicit selection, but we will switch the default domain setting to boundary and group by continuous tangent. So it will find all the surrounding parts, and this is, let's say, outer boundaries. And then we can go back to the heat flux interface and select outer boundaries. You can set up a convective heat flux if you wish, let's say constant value if it suits you well. And then you can go for an active cooling setup, like switching this to external forced or natural convection. So if you are into an external forced convection and let's say it's rather a cylinder in a cross flow, so this plate should be changed to a cylinder in cross flow. So if you have this type of configuration that's much more suitable for this setup, then we could set up this diameter. So we can set up 0.045. You can set up the velocity of the fluid, what type of fluid do we have, air, water, or something else, and then set up the correct and much more precise heat flux and heat transfer coefficient based on some empirical relations here. So here in the equation section, you can always check how the heat transfer coefficient, this H, is calculated. So technically, yeah, the Reynolds and the Prandtl number, they are evaluated through these geometric entities. And then, since we have more than one physics interface, so this electromagnetic heating appears here. So you can add and couple the heat transfer to the AC/DC fields, and that's it. That's the whole setup you need to do. And then we can add another study to calculate the maximum temperature, the temperature distribution through these simulations. So that's how easy to do that. Okay, so going to the optimization side. So this is the heat transfer part. So if we go into our model here and go back to the presentation. So we wanted to talk about a little bit on optimization. So if we go to the model library, and we go for motor optimization. There are more than 800 of these models here available online, so you can check all the availability here. It's a very nice search window, and you can download the documentation like what I'm going to do right now. So we can go and look for the documentation here. Optimization. So let's do this here. So this is the initial setup. So this is the same that we have seen before. So all the parameters, all the properties, geometry parts are imported from the part library. And we are going and look into the different slots and the ratio and the angle of these magnets compared to the initial one. Technically, there are just a few, let's say, micrometers, maybe a few millimeters that are available for moving these things around inside here. That's technically a typical scenario here, and this model takes into account this one also. So there are no huge deformations and displacements in the model, since that's not viable when you are dealing with a real world motor design. So these are the variables. So these can be changed during the optimization algorithm. Different distances and angles, the electric angle also. Okay, and here you can see a snapshot. So here in the horizontal axis, you can see the maximum magnet area. So that's what is seeable here, that you can see here. On the vertical axis, that's the average torque. And you can see, of course, more magnets means higher torque as expected. So that's one outcome from the optimization, but it's quite significant. It's more than 20% increase in the maximum torque. That's a lot. And here you can see another version. So here on the horizontal axis, you can see the number of sectors. And here on the vertical axis, you can see also the average torque, how it's changing for different scenarios. These dashed lines means that you have 6 slots per sector. Yeah, the maximum is somewhere here. So when you have 6 sectors with 6 slots, maybe that's the maximum torque that you can take out from this motor design. Otherwise, it will decrease if you increase the number of sectors. And also, on the horizontal axis, the number of sectors, and on the vertical axis, the torque, and different design scenarios, that how many slots per sectors, 3 or 6. And it seems that the maximum torque can be utilized when you have, yes, the 6 sectors and 6 slots per these sectors. So that can be achievable here. And this model is utilizing that one, electric motor parameter optimization. So let's look into that one. So if we go into the application library and we are looking for that one, let's hope we can find that one here. All right, just simply download it from our website. That's super easy to do that. Okay, so we have the model opened up here. So let's go into the model. So we have rotating machinery, as we have seen previously. So the geometry is imported from the library. We have different coils, 1, 2, and 3, based on the optimization setup. We have the regions defined by the BH curve. We have the magnets, the permanent magnets, and you can see the direction is parameter. It's parameterized since the optimization algorithm will change their position and size. So this will change also. It's calculated from the geometry setup here. And we have the torque calculation setup here, as always. And from the default geometry side, we have, yes, the rotating domain. That's the rotation angle defined here. So that's the physics setup. And from maximize average torque, there are different scenarios here. So here one optimization setup here. So here this is the expression, T arc. This is the torque, number of solutions. So the number that we are optimizing for. So that's the expression, that's the objective function that we are using, and this will be minimized. And here you can see the 6 parameters that can be used, and those parameters will be changed during the optimization algorithm. And the same goes from the minimum torque. There's another torque calculation. The same goes for the objective function. Then the maximizing the average torque. And here it's combined. The optimization is combined with the parametric sweep, where we sweep the area of the magnet. And here another one where we sweep the slots per sector and the sectors. So there are different scenarios for different needs. And here we can see the results here in comparison. So yeah, the maximum appears here when we have 6 slots per sectors, and we have 6 sectors. Otherwise, the maximum torque is lower than this value. So that's in combination with an AC/DC module with an optimization module, so you can easily combine different models and different modules.